Okay. Compiling was a very basic thing that was done. But now building is kind of a bit more complex in how it does things, and this is where your make files and things like that come into play. And that's what this is going to cover. Because compiling projects can be such a complicated and repetitive process, a good IDE provides the means to abstract, simplify, and even automate software builds. Unix and its descendants accomplish this process with a Makefile, a prescribed recipe in a standard format for generating executable files from source and object files, taking account of changes to only rebuild what's necessary to prevent costly recompilation. One interesting thing to note about Make is that while it's generally used for compiled software build automation and has many shortcuts to that effect, it can actually effectively be used for any situation in which it's required to generate one set of files from another. One possible use is to generate web-friendly optimized graphics from source files for deployment for a website, and another use is for generating static HTML pages from code rather than generating pages on the fly. It's on the basis of this more flexible understanding of software building that modern takes on the tool like Ruby's Rake have become popular, automating the general task for producing and installing code and files of all kinds. So you see IDEs that can, like Eclipse and so on, NetBeans and whatever, that compile your whole Java program for you and runs it. Whereas Make does this for you, but at a command line level. And you'll see a lot of utilities for Linux that use a Makefile and have it in the repository for this reason, because then it's a bit more portable to build your project and program than it is sometimes for other implementations like doing a Visual Studio project or an Eclipse project. Anatomy of a Makefile. The general pattern of a Makefile is a list of variables and a list of targets and the sources and or objects to use to provide them. Targets may not necessarily be linked binaries. They could also constitute actions performed using the generated files, such as install to instate built files into a system, and clean to remove built files from the source tree. It's this flexibility of targets that enables Make to automate any sort of task relevant to assembling a project build of software, not just typical parsing, pre-processing, compiler proper, and linking steps performed by the compiler, but also running tests, compiling documentation, source files into one or more appropriate formats, or automating deployment or code into a production system, for example, uploading to a website via a Git, push, or similar content tracking method. Yeah, I mean, Makefiles, again, are very heavily used. So the build targets thing, I think, yeah, there are quite a few projects that I've seen that alter the build that you get based on the build targets that you get, and I think I'll get into it after we finish up with the Makefile section. An example Makefile for a simple software project might look something like this. So you've got the all example, and then the example has main O, example O, library O, GCC main O, example O, library O, example. So this example basically targets a build of main.o, example.o, and library.o. So it's going to go through and run the main.o build target, which is GCC main C to main O, and then example O from up here, it's going to GCC example C to example O, and then our library O is going to GCC library C to library O. So it's going to pull these files in, so main.c, example.c, and library.c, and then it's going to turn that into this file, and now this is your output that you're getting. And then these are going to take these input files and push it out to example. Now sometimes you can give it a different build target as noted here. So then install will just copy example to user.bin, so I can go make install and it'll just run this part, and then I can make clean and it'll remove all the ARM examples. The above isn't the most optimal Makefile possible for the project, but it provides a means to build and install linked binary simply by typing make. Each target definition contains a list of the dependencies required for the command that follows. This means that the definitions can appear in any order, and the call to make will call the relevant commands in the most appropriate order. Much of the above is needlessly verbose or repetitive. For example, if an object file is built directly from a single C file of the same name, then we don't need to include target at all, and make will sort things out for us. Similarly, it would make sense to put some of the more repeated calls into variables so that we wouldn't have to change them individually if our choice of compiler flags change. A more concise version might look like the following. So CC is GCC. Our objects are main O, example O, and library O. And our binary is example. So we can call example on all. An example will bring our objects in, and then our objects go from the CC to the objects, and then output the binary. Our clean will clean the binary and clean the objects, as noted here. And then our install will install the binary to user.bin. So we could rename the binary and it would just keep track of it without much thought. So this Makefile is just a short example. A more complex example, as noted, that would change things would be like going back to a Pokemon project. If I go into Polished Crystal here and go to the Makefile, I can edit it. And you can see we've got all our variables set forth up front here. So if we've got a few different flags. We've got faithful, no RTC, monochrome, noir, HGSS, and debug. And so this changes like different goals and things like that. It adds in different flags onto it as well. So I can continue to add, I can compile a faithful build which changes certain stats with a no RTC build which removes real-time clock functionality and make it monochrome here. And then I would have a ROM with all these features in it because I've added these flags to make, and this changes, in essence, the build target of what I'm building. And then I could make a debug ROM with HGSS colors and make it faithful. Or I could take noir colors, make it faithful, and debug. And this customizes the way we build the ROM because of the more fleshed out tweaking we can do with a Makefile that will change the the compiler command on the fly. So if I go to, for example, let's see, RGBDS up here. Let's see. So you can see clean, tidy, crystal, faithful, no RTC, debug, Chrome, free space. So if I go to tools, I could build tools. This isn't included up here, but you get the idea. And each of these is going to call crystal, obviously. So in crystal right here is ROM name version. So I could change, if I go up here, let's see, where was it? Those are our crystal objects. Where did our name go to? Name up here, so we can change that, these two, and change what we're building. So if I go back to, let's go into this one. Did I change that one? I didn't. So I could go into here and I could add Canto to it, and then it would build polished Canto crystal rather than building just polished crystal. And then I can go back down through here and I wouldn't have to think about building any of it otherwise from there. So you've got a lot of different things in here too. So like the clean will remove the GBC, the map, the sim files, and all the crystal objects, which can be useful in this case that you're cleaning it completely, because sometimes as you're compiling over and over again, you get some cruft from previous builds that builds up and causes errors in the ROM. So occasionally cleaning out and recompiling and starting over again will refresh the images that are generated and are compiled into the ROM so that you can actually get a proper build of what you're building. So we've got our GBC right here that does the RGB link and so on. You've got your image generation conversion and your object building. Let's see, where was... And obviously you can see that there are even some regular expression stuff going on, or wildcard implementation stuff, so that you don't have to call every file, but you can go into the makeup here and it will make these objects with one line without you having to add separate lines for each individual object. So in the interest of automation, however, it's instructive to think of this a bit more generally than just code compilation linking. An example could be for a simple web project, including deploying PHP to a live web server. This is not normally a task people associate with the use of Make, but the principles are the same. With the source in place, ready to go, we have certain targets to meet for the build. PHP files don't require compilation, of course, but web assets often do. An example that will be familiar to web developers is the generation of scaled and optimized raster images. From vector source files for deployment to the web, you can keep in version your original source file, and when it comes to deploy, you generate a web-friendly version. Assume this particular project that there's a set of 4 icons throughout the site, size by 6464. We have the source to hand in SVG vector format, safely tucked away in version control, and now need to generate the smaller bitmaps for the site ready for deployment. We could therefore define a target icons. For the dependencies and type out of commands to perform, this is where the command line tools in Unix really begin to shine in use with Makefile syntax. So you've got icons, create these. Then you've got create PNG, create SVG, convert SVG, and so on. Read, and then it does convert, and then crush. And it just kind of repeats that for every one of them. With the above done, typing make icons will go through each of the source icons file in a bash loop, convert them from SVG to PNG, using ImageMagic's convert, and optimize them with the PNG crush to produce images ready to upload. A similar approach can be used to generate help files in various forms. For example, generating HTML from Markdown source. So you can mark down and output it to HTML, like so. Perhaps deploying a website with git push web, but only after the icons are rasterized and documents converted. So you can add icons and docs, and then it'll git web push. So it'll build these targets and then push to the web. More compact and abstract formula for turning a file of one suffix into another, you can use the suffixes pragma, as we've seen in the polished crystal Makefile, to define these using special symbols. The code for converting icons could look like this case. In this case, refers to the source file, and then and then to the file name, no extension. So SVG and PNG. So SVG PNG convert source to what? Output. Source to output, and then the target. So then you can list all your files up here, and then it will be able to convert from the SVG to that, which we saw in otherwise. Variety of tools exist in GNU Auto Tools toolchain for the construction of configure scripts and make files for larger software projects at a higher level. In particular, AutoConf and AutoMake, the use of these tools allows generating configure scripts and make files covering very large source spaces, reducing the necessity of building otherwise extensive make files manually, and automating steps taken to ensure the source remains compatible and compilable on a variety of operating systems. And then, so there are a lot of make options, and even then going back to projects, and then we'll go into a different folder this time. So if we look at DWL's Makefile, there are a bunch of different options in here too. So we've got our flags in here, and then we are calling our different objects in here for this. And I don't remember which project it was, but you can see our... So one thing with certain projects is, like as noted with it, sometimes you want to just copy a file. So if I call makeconfig.h with DWL, it'll take this template config.h file and create a config.h file that I then run my configuration in and go from there. Now, if I just type make, let's see, all DWL, so if I go down to DWL, it will do things and do things. One thing it'll make sure it does is create a config.h. So if config.h is not created already, it will create that. And then otherwise, it'll skip config.h because I've already have one and I've already changed it. Config.mk, let's double check where that was. Yeah, that's not in here. But config.mk gives certain make flags that will run specifically for Wayland to compile X-Wayland functionality. So I can exit out of here. I don't remember where it was. I think there was one that I edited, changed up in a Makefile because it used GCC, and I changed the CC to be muscle C. Muscle GCC, because muscle G has an option to do GCC linking so that you can compile programs with muscle rather than GCC. So then you can say, hey, it's not GNU, I compiled it with muscle. But anyway, I just can't find where it went to. So it's things like that where you've got, all you're doing is messing with a script pretty much from the get-go. And it makes things simplified to work with. So like even Blasphemer has a Makefile. We can compile blaspheme.wad and it'll call doText, and it'll also call up lumps, and lumps runs a blasphemer sound curve, blasphemer sound curve.py, and yeah, so you can get your blasphemer wad output, and it does a blasphemedm.txt. But anyway, so you've got a whole bunch of tooling options, and then here's where the install matters. You can make install, and then it'll install to the target there, and then go from there. So you're very powerful, very, very powerful. If you enjoyed the video, then like, comment, subscribe, feed the algorithm, boost the video up, share this video with your friends. If you found it informative or you just want to chat, I've got plenty of places in the description, Discord, Guilded, and what have you. Check those out, and I will see you guys in the next one.